The third poster is towards a framework for one-sided RDMA multicast. The author is Xin Zhe. He's currently a first-year PhD student at the National University of Singapore, and his research interests are in software-defined networking and programmable data planes. So even in this case, Xin Zhe, the stage is yours.
Thank you, Spatch Channel, for the introduction. So welcome everyone to the talk. So I'm Xin Zhe Khooi from the National University of Singapore, and today I'll be sharing about our preliminary findings towards a framework for one-sided RDMA multicast. Okay, first we will look at group communications. So there are various applications that exhibit group communication patterns in data centers, like file system replication, distributed coordination, so on and so forth. The easiest way of doing this is through Unicast, whereby the sender will have to initiate individual connections to each receiver. However, this is wasteful and inefficient use of network resources. A better way of doing this is to perform multicast to the entire group. Here, the sender only needs to send once. Obviously, multicast offers efficient link utilization as well as accelerating application performance. With multicast out of the way, next we will talk about RDMA. As we are all aware, the end of Moore's law is on the horizon, thus every CPU cycle matters more than ever. We see the trend of offloading network I/O from the CPU to conserve CPU cycles. Notably, so there are RDMA NICs that offloads the network stack onto hardware. It is also evident that data center operators are shifting towards RDMA. In RDMA, there are two sets of operations. So one is one-sided. So in one-sided, there are operations like read, write, and atomic. So these operations do not require the CPU, and you can perform a direct memory access on the remote side. However, to do direct memory access on the remote side, so it involves a unique set of connection parameters. So the parameters are the queue pair number, the packet sequence number, the remote key, and the remote address. These connection parameters are unique per receiver, per connection. And because of this property, multicast is not possible because of the per receiver, per connection property. On the other hand, we have the two-sided send and receive operations. So these are similar like other kernel bypasses like DPTK or XDP. So whereby the CPU is actively involved to process the packets, and because that it does not require any unique connection parameters, it supports multicast. So here, we think that whether is it possible to have both one-sided operations to support multicast. So what we want is to have zero CPU overhead and multicast at the same time. This is what the question that we ask in this work. Before we dive further, let us look at how one-sided RDMA works. First, before performing the transfer, the sender will have to reach out to receivers to get the connection parameters for each of them. Then, once the sender has the parameters, it can then start the transfer to each of the receivers. So this is in the context of Unicast. So what if we want to do it in the multicast way? Is it possible? So suppose that the sender tries to initiate the transfer using a global parameter that is specific to the group. So here in this case, group X. However, this requires us to modify the behavior of the receiver's RDMA in order to accept the global parameter. Unfortunately, the RDMA NICs are fixed function, and we cannot really do anything about it. So none of the receiver will accept the packets. Now, so in this case, how can we then work around this fixed function RDMA hardware to enable one-sided RDMA multicast? The key idea is to leverage P4 programmable hardware to augment the fixed function RDMA NICs. We leverage the switch to perform the mappings for each of the individual receivers at the last hop. That way, we can trick the receivers that it was a unicast packet instead of a multicast, but in reality, it was a multicast. If we look at the framework as a whole, so first, the sender would have to talk to a coordinator about the multicast to request a multicast transfer. Then the coordinator will have to talk to the receiver's RDMA NICs involved in the group to establish the connection and also retrieve the connection parameters. Then these connection parameters will be configured onto the switch. And finally, the coordinator would signal the sender. Following that, the sender can begin the multicast transfer while the switch performs the connection parameter mapping. Once the transfer is done, the sender signals the coordinator, which then reaches out to the receiver to tear down the session. Apart from the P4 programmable switch, we can also leverage on some of the RDMA NICs that come with P4 programmable pipelines. Some of the examples are the Mellanox Bluefield 2 DPU NICs, or even the recent Intel Mount Evans IPU. So by combining both P4 programmable switch and the NIC, we can further scale out this solution, given that there are only limited amount of memory on the programmable switch. To do that, we perform a division of labor, whereby the switch only focuses on multicast, whereas the P4 programmable pipelines on the RDMA would perform the connection parameter mapping right before the RDMA transport hardware. Well, what I have presented here are just some of the preliminary findings that we have. So more details can definitely be found on the paper and plus the evaluations. There remains a lot of work to be done. So for instance, in order to make this framework feasible, we still need to implement it we still need to implement the API to make it available as a service to generate applications. On top of that, there's still a lot to do in order to study the interaction between multicast and PFC. PFC is what makes lossless Ethernet possible. On the other hand, how to do reliable transmission in the context of RDMA plus multicast is still to be further studied. And lastly, to make this solution truly feasible, we also need to consider scalable multicast routing solutions such as source routing. With that, I conclude my presentation and I'm open for questions. Thank you for your time.
Cool. Thank you very much. It was very interesting talk. Also, I liked the open questions that you raised at the end. I think they are very, very interesting. Let me check. Apparently there are no other questions. So I will have just a quick question. So you mentioned that in order not to scale the system, you need to include also the cooperation between the NIC, the smart NIC, and the switch itself. Do you think this is really scalable? Because I guess for every multicast packet, you need to send a message for every switch to include the set of flows that needs to be mapped for every multicast group. So how do you think this is this can be scalable in a large deployment?
Yeah, that's a good question. So for that, I guess it depends on the trade-off that we want to make here. So let's say if you were to perform some really, really large transfer and you do not really want to sacrifice any CPU performance, definitely to spend that initial latency to set things up is definitely worth it. And plus, if you look at the memory consumption on the NIC side, since these P4 programmable pipelines on the NIC, they have more memory. So for that, it's actually less expensive, I would say negligible in terms of the actual memory consumption.
Okay, cool. I just have another quick question. I think we are a bit late, but I'm curious also for this question. So you mentioned in the poster that the prototype on the Bluefield is not using the P4 hardware pipeline, so you just emulated it on the CPU of the NIC. Is that correct? Do you right? So no.
So currently the Bluefield NICs officially they do support P4, but at the time of writing we were not able to get the actual P4 target that is targeted for that NIC. So eventually we installed BMV2 on that NIC. So so on the ARM cores, so the BMV2 is running on the ARM cores of the Bluefield NICs.
Okay, I see. And the support, the P4 offloading is not available yet in the blue field.
Yeah, I guess so.
Okay, I see. Thank you. Thank you very much, Xin Zhe.
All right, thank you very much.
Bye bye.